Yeah, so our third speaker for this section is Eva Halacheva, also from Northeastern University, who'll talk about Schubert calculus via Lagrangian correspondences.
Thank you for the introduction. It's great to be here, and I would like to thank the organizers for inviting me. So I should mention that this is joint work with Alan Knudsen and Paul Zinjustin. You'll see their names pop up in some of my slides as well, a little bit later on. I have to say I'm a little bit sad because this is a Poisson workshop, and I have some symplectic and Lagrangian structures in my talk, but as far as I can tell, nothing here is Poisson per se. So if you find something Poisson, please let me know. That is sort of more of an epitome of the Poisson structure. So, okay, let me start with a little bit of the overview of what I'm going to talk about. So I'll start with some background and motivation for Schubert calculus and what are the classical questions there. And then I'm going to talk about a branching, which is in cohomology, but more of a combinatorial nature. And then I will explain how, with my collaborators, we would like to interpret it and upgrade it to a more geometric picture. And I'll mention at the end some results towards this goal so far. So here's the setup. So we're starting with partial flag varieties. So we have a complex algebraic group G, and let's fix a pinning for it. So namely a torus inside a Borel inside G, and then W will denote the Val group for our group G. And so for any parabolic P, we have the quotient G mod P, which is a smooth projective variety. And the torus acts on that, and the torus fixed points can be identified with the quotient of the Val group by the parabolic Val group, either as left or right quotient. And so what I'm interested in generally is studying the equivariant cohomology of such a partial flag variety. So the torus equivariant cohomology, and operations such as multiplication and restriction. So of course, those are understood well abstractly, but I would like to consider them in a nice basis, which I'll talk about in a moment. So for instance, here the first operation is multiplication in the cohomology, and the second operation is restricting from one partial flag variety to another, where H here is a subgroup of G with a compatible parabolic Q and torus S. And so this is the completely general setup, but I would like to focus more concretely on the case where G is of classical type. So it's of type AN, BN, CN, or DN, and we have a maximal parabolic. And in that case, the partial flag variety is usually called the Grassmannian of that particular type. So for instance, we can consider the Grassmannian of K-planes in N space. This final line here is giving this description, which is the quotient of the general linear group by the parabolic, which has blocks of size K and N minus K. And similarly, we can consider the symplectic Grassmannian, which is an analogous quotient of the symplectic group by such a parabolic. And this can be realized as isotropic K-planes in some even dimensional complex space. Okay, so now that I've set the stage, let me talk about this nice basis that I mentioned we want to consider for the cohomology of a partial flag variety. So this is the basis of Schubert classes. So let's take any of the torus fixed points of our partial flag variety. So going back to the general setting, then a Schubert class indexed by that point is given by the B minus orbit of the P inverse point in the partial flag variety. B minus here just denotes the opposite Borel for the Borel B. So we take the closure of this orbit, and the class for this variety is called the Schubert class, indexed by pi. And so as I promised you, these Schubert classes really generate the equivariant cohomology of the partial flag variety as a module over the equivariant cohomology of a point. And so one of the classical questions for these Schubert classes is to study their product and the structure constants for their multiplication, and understand their symmetry or certain positivity properties. And even more classically in the representation theory, if you consider in particular the Grassmannian of K-planes, and here we look at regular cohomology, so non-equivariant, then these structure constants are the Littlewood-Richardson coefficients. So they're giving us precisely how highest weight tensor products of highest weight irreducible representations decompose again into irreducibles. And so here's a even more specific example for the Grassmannian of two planes in 4 space. For the torus, in this case, we have that the equivariant cohomology is a polynomial ring in 4 variables. And so the Schubert classes, I mentioned, are indexed by elements of the Wahl group quotient. And in this case, we can realize them as partitions. And so suppose we're multiplying the Schubert class indexed by a box with another Schubert class indexed by a box. You can decompose it in this way, where the last term only appears in the equivariant setting. If you work non-equivariantly, you only see the first 2 terms. Okay, so let me mention now a result for understanding these coefficients. So there's a theorem by Knudsen and Tao from 2003, which has had multiple extensions since. Again, we're working in the Grassmannian setting, and in that case, the Schubert classes can actually be indexed by binary sequences. So a binary sequence that contains k zeros and n minus k ones is what this notation means. And so to understand the structural constants here, we're looking at a certain Boltzmann weight constructed using these combinatorial puzzles that I've drawn at the bottom, some examples of. So suppose we want to find the mu coefficient of lambda times mu. So then you put lambda, mu, and nu on the boundary of such a triangle. And there are certain rules for how you can fill in this triangle. And then once you filled it, using R matrices from the 5-vertex model in statistical mechanics, this gives you a coefficient for nu. So in this example here, it's actually the same product we saw in the previous slide, but now I'm using the alternative and equivalent indexing with binary sequences. And you can see that the first puzzle corresponds to the first class, the second puzzle corresponds to the second class, and the third puzzle, which has this blue or equivariant piece, gives us the coefficient here. And all the coefficients should be living in equivariant cohomology of a point. There might be more than one puzzle adding up to each of the coefficients, but in this example, we only have one for each. Okay, so this is sort of the classical problem addressed using puzzles of multiplying Schubert classes. So what I'm interested in is studying the inclusion of the symplectic Grassmannian into the usual or type A Grassmannian. And this inclusion is realized through the thinking of the symplectic group as the 6 points of the general linear group under a certain involution, which I just write down here. It's not, the details are not too important, but this is what happens to a matrix. And the fixed points under this involution are the symplectic group. And this gives us the inclusion of these Grassmannians. So if you think about the pullback of this inclusion in equivariant cohomology, we're interested in what happens to a Schubert class when you expand it again into Schubert classes. And how are these coefficients determined? And so there's some previous work by Pragach and Joshkun, where they work with either with the Lagrangian Grassmannian or with the more general Grassmannian, but non-equivariantly. The way we address this problem is, so first of all, we're interested in the map on the right side. So this is the pullback of the inclusion. But since both of these Grassmannians are smooth projective spaces, we have Corwan injectivity. And so we know that their cohomologies inject into the equivariant cohomologies of their torus fixed points. And instead, we can work on the left side instead. So we can work with just torus fixed points. And there's a formula by Anderson, Janssen, and Zergel, as well as Billy independently, that describes how you can restrict to torus fixed points the Schubert classes. So this is our approach to the showing the following theorem. So this pullback map from the Grassmannian to the symplectic Grassmannian in their cohomologies can be described again using puzzles. And these are W of such a puzzle is, again, a certain type of Boltzmann weight, where we've incorporated the R and K matrices now of the 5-vertex model. And remember, we realized the inclusion using a certain involution on the general linear group. And this, in fact, can be seen as an involution on the puzzles coming from this Grassmann duality of the isomorphism between the two Grassmannian varieties. And so we get a certain involution on puzzles, and we only consider the puzzles fixed under this involution. And they allow us to compute the coefficients here. So I'm giving this more as a motivation. I won't include the general details in this setting, but let me just give you an example of how this works. So here is a Schubert class for the Grassmannian, and we pull it back. Remember, we start with binary sequences. Once we are in the symplectic Grassmannian, the indices generalize to ternary sequences. So things are indexed by 1, 0, and 10. And here's an example of such an expansion, which corresponds to these puzzles. Now, the goal is to generalize this somewhat more combinatorial and homological or cohomological puzzle rule to the 6-vertex model in statistical mechanics, as well as to understand the underlying geometry to obtain a more generalized puzzle rule, perhaps. So let me move on to the more geometric side of this story. So to do that, let me introduce Lagrangian correspondences. So a Lagrangian correspondence between two symplectic manifolds A and B is just a Lagrangian cycle in -A times B, where by -A I mean we are negating the symplectic form on A. So this is just a linear combination of some varieties in -A cross B. And if we furthermore have a torus action as before, under which this Lagrangian cycle is invariant, then such a Lagrangian correspondence induces a map in localized equivariant cohomology from A to B. So localized just meaning we're tensoring with the field of fractions of the equivariant cohomology over a point. But so the key property to remember is the Lagrangian correspondence gives us a mapping cohomology. And our symplectic manifolds, for our purposes, are going to be the cotangent bundles of the partial flag varieties in this picture. Okay, so some examples of such Lagrangian correspondences are symplectic reduction. So if you have a Hamiltonian action, then we can consider the moment map and the preimage of a regular value under the moment map gives us another manifold Z, which is a Lagrangian cycle in the product of our original symplectic manifold X and the GIT quotient obtained from the regular value, which is also a G fixed point. So symplectic reduction is an example of a Lagrangian correspondence. Another type of Lagrangian correspondence is given by the Mollico-Kunkov stable envelopes. So suppose we have a symplectic resolution with a circle action. So S here is a circle acting on X, and we take a fixed point component for this circle. Let's call it C. Then Mollico and Kunkov give us, via so-called stable envelope construction, another Lagrangian cycle, which is the closure of the attracting set of C under the circle action, together with some additional components which are themselves attracting sets. And the additional components that we add cause L to behave nicely under composition. So when we try to compose Lagrangian cycles, for instance. So let me talk about a few other correspondences. So more generally, we can think of a correspondence which is not Lagrangian, but let's think about correspondences coming from graphs of morphisms. So if we have a morphism between two oriented manifolds, now not necessarily symplectic, then we can consider the graph of this morphism. And so that graph gives us a correspondence between the two manifolds, which induces the pullback map of our original morphism in cohomology. So some examples of this are, if you consider the diagonal inclusion, then the graph or the transpose of the graph of this map induces multiplication in cohomology. Or if you consider the graph of the following inclusion, so this is so here by flag of JKN, I mean another instance of a partial flag variety, which can be realized as J planes inside K planes inside N space. So this includes by into the product of the Grassmannians by forgetting the K plane or the J plane. So this inclusion induces another multiplication on the level of these Grassmannians and flag varieties. And finally, for our example of interest, the inclusion map of the symplectic Grassmannian into the Grassmannian, its graph induces the restriction map in cohomology. Alternatively, we can work in equivariant cohomology here. Okay, so so keeping in mind these correspondences coming from graphs, let me talk a little bit how we're going to lift our original function to these using these types of correspondences. So suppose again we have two manifolds A and B, and we started with a function between them. Then we have the following commutative diagram in terms of correspondences. So we have the graph of our function, which is a correspondence from B to A. And here transpose is just for technical reasons because I'm going from B to A, not from A to B. So I hope that doesn't alarm you too much. And iota B and iota A are the inclusions of each manifold as the zero section of the cotangent bundle. And so here I'm taking the graphs of these inclusions in the zero section on each of the vertical lines. And finally, on top, we have the conormal bundle of the graph of our morphism. And so this diagram commutes if you compose these correspondences. And so this allows us in particular to upgrade from our manifolds to their cotangent bundles and go beyond functions to more general correspondences, which don't necessarily come as the graphs of functions, as well as we can factor. So for instance, this the conormal bundle, we can factor it into other Lagrangians, which are not necessarily conical here. And look, oh yes.
It's a 5-minute warning.
Okay, thank you. That's great, I think, good. So, so these correspondences that I mentioned then induce maps in cohomology, which is torus and dilation equivariant, dilation coming from working in the cotangent bundles. And in particular now, to understand the pullback on the lower row, it suffices to understand this the map on the top, which is in this symplectic setting, because now these cotangent bundles are symplectic. In particular, if a class beta goes to a class alpha, what happens on the bottom is the class beta divided by the zero section, the class of the zero section goes to the class alpha divided by the class of the zero section. Since we are dividing by zero sections here, we need to work in localized cohomology. Okay, so this is the more general setup. So now let me talk about how we go to upgrading this in the context of partial flag varieties and Grassmannians more specifically. So, so we're working with our cotangent bundle, and suppose we have a regular circle action, so one with isolated fixed points. And suppose one of those fixed points is lambda. Then using the stable envelope construction, we get a so-called mocycle or Mollico-Kunkov cycle, which is whose class is going to be a generalization of the Schubert class we saw earlier. So this is given by the closure of the Bielinitsky-Birula strata for lambda, which is the attracting set for lambda, or the conormal bundle, the Brucha or Schubert cell, together with some other closures of other BB strata indexed by mu, where mu is less than or equal to lambda in Brucha order, with some non-negative coefficients. And so this gives us a class in the equivariant cohomology of the cotangent bundle, so generalizing the Schubert classes. And remember, because we want to divide by the zero section, it is more natural to consider the Segre-Schwarz-McPherson class, which is the MO class divided by the zero section. And from these SSM classes, we can recover the Schubert classes in the classical Grassmannian picture in the following way, where this H bar coefficient is just related to the dilation action. Because the cotangent bundle homotopy retracts to G mod P, the dilation action is just trivial, and that comes out as a variable H bar. But the moral here is that we can recover the classical picture from these more generalized classes on cotangent bundles, as well as the structure constants. And so for my final slide, let me mention our theorem in progress with Knudsen and Sint-Justin, which is saying that so we want to construct a correspondence between the cotangent bundle of the Grassmannian and the symplectic Grassmannian, which gives us the map we want in cohomology. And in fact, we're able to do so, where lambda here is a fixed point. And so that gives us the corresponding Mollico-Kunkov class. And the first two Lagrangians here are stable envelopes. And the last one is a symplectic reduction. And these together with the 6 vertex R and K matrices allow us to get a more generalized puzzle rule. I think I'll stop here, and thank you.
Thank you very much, Eva. So let's all give Eva a round of applause. Don't forget your emojis. Round of applause with emojis. Excellent. Thank you.